Welcome to the course Introduction to Algorithm. My name is Saurabh Mukhopadhyay. I am a faculty member at IIT Kharagpur. I am lecturing this course. This lecture is about data structure augmentation. This is lecture number 10 of this course. In this lecture, we will cover what do you mean by data structure augmentation. So, we will discuss basically three problems. First one is dynamic order statistics problem. So, dynamic order statistics problem means we have already seen the order statistics problem. So, we have given a set of n numbers and we need to find the ith smallest element. So, that was the order statistics problem we have discussed. But that in the our order statistics problem that set was static, I mean fixed. We have given n numbers and we have to find the ith smallest element. But here it is a dynamic order statistics problem. This set is dynamic, that means any record can join any point of time, any record can delete from this set. So, the challenge is given a dynamic set of records, we need to find the ith smallest element of the key value of the record. Okay. So, we have given n record, at some point of time there are n records and this set is dynamic, we have to find the ith smallest element. So, that is called dynamic order statistics problem. So, for this we need to search for a data structure. Now, instead of searching for a new, instead of design a new data structure, what we can do? We can take an underlying data structure which we know to be good, like balanced binary search tree. Then we take that data structure and we can do some add some extra field of information there in the node, and then we can see whether that will help in our problem. So, that is called data structure augmentation. So, we will discuss this in more details by taking this problem, dynamic order statistics problem. Then we will see the interval search problem, and then finally we will see another problem which is called fixed universe successor problem. So, there we will have a new data structure which is Van Emde-Boas data structure. So, that we all will be covered in this lecture. So, let us start the lecture. So, let us start with the problem what is called dynamic order statistics problem. So, or we say this is OS means order statistics. So, this set is dynamic. So, we have seen the order statistics problem is given a n numbers, we need to find the ith smallest number. That means we need to find a element number whose rank is I. Okay. And another problem is, suppose we have given n numbers and we need to find the rank of n, given an element we need to find the rank of that element. So, these two problems we have to discuss, and but here the set S is dynamic. That means this set any time we should able to do the insertion of the elements and we should able to delete the element. These two operation makes this set dynamic, insertion and deletion. So, this is kind of we are storing some records and each record is associated with a key value, and we have to have a data structure for this record for considering the key values to store, so that the finding the ith smallest element will take faster time. And this set of the records is dynamic. So, that is the problem, that is called OS select problem. So, now to suggest there are two ways we can think for a very new data structure from the scratch, but and also but that sometimes is difficult to think of. Instead of that, if we can start with a good data structure we know, because we have seen many good data structure like balanced binary search tree, that is red black tree, and then we take that data structure, underlying data structure, and then we can add some information in the node for which can help us in this problem. So, that we are going to do, and that technique is called data structure augmentation. So, let us take an underlying data structure. We will use the red black tree, which is we know it is a balanced binary search tree, which is good in the sense that it is balanced. Okay. We use the red black tree for this set S, which is a dynamic set and it has n elements say n records, and each record is associated with a key value, and based on that key value we will do this storing. I mean, we'll form the tree. I mean, we'll form the red black tree, and the key value is the key value of the record, like this. And here in this node, each node we want to have a extra bit of extra information, that is the size of the tree rooted at that node. We keep the subtree size in that node. That means size of the tree rooted at that node. So that information we want to keep, and we will see how this information will help us to find the ith smallest element or the order characteristics. And this is for finding the given element, what is the rank of this. So this we will not discuss, we will discuss on this algorithm OS select, that is the on this set, this dynamic set, how to find the ith smallest. So now we store these records in the binary search tree way with this key, and along with the this extra information we are going to maintain in this node, in each of the node, that is the size of the tree rooted at that node, or in other words we keep the subset size in the node. So that is the size of the. So let us take an example. Suppose these are our key values M, C, A, F, D, H, P, N, Q. These are our key values, and we are storing this in a binary in a red black tree. And this is a red black tree, means it is a balanced binary search tree. So it is a binary search tree. We can see if we just consider the order of A, B, C, D in the alphabetical in the alphabet, then it maintains the binary search tree property. And we can make the color of it. We have nils over here. So nils I have not drawn here. So nils you can just visualize here. We have a nils over here. Okay. So now we can just make the color. We know the red is root is black, and these nils are black basically. Then we can make the color. So we can do just like we can make it black. And then we have to make it black, and then we can just make these two black, and these two also black, and we can just make this red and remaining all are black. I think that will help us, because if we have a this black height, if we start from here to here, we have a 2, 3. 2, 3, 4, and if we start from here to here 2, 3, 4, that is fine. So yeah, so make this node to be black, red, and others everything you make it black, every node to be black including the nils. So that is a red black tree. Anyway, you can just verify it. Okay. Now we have to maintain another bit of another information in the node, that is called size of the subtree rooted at that node. So this is the convention. The idea is we put the size of nils to be 0. So here are nils, and then we define the size of x, size of a node to be size of left subtree plus size of right subtree plus 1. Okay. Now here in this node we have 2 nils over here. We have 2 nils over here. So this is 2 nils over here. So we have 2 nils over here. Now nils are size 0. So if we apply this formula, size of this node is basically size of the left subtree, which is nil, which is 0 plus 0, and then plus 1. Plus 1 means the root, I mean the subtree rooted at this. So this size is 0 plus 0 plus 1, 1. So similarly 1, 1, 1, 1. And now what is the size of this node? Size of the left subtree plus size of the right subtree, which is 1, both are 1 plus 1, and then plus 1 this node. So this is the 3. So 3 nodes are here which are hanging the subtree rooted at this. Similarly this one, similarly this one, and when we consider the size of this node, that is basically size of left subtree, which is 5, size of right subtree, which is 3, and this plus 1. So 9. So that means total 9 nodes are hanging in this subtree rooted at this node. That is the original tree. So, this is the way we maintain the size of a node. Okay. Now, we will see how this size will help us to find the ith smallest element. So, just to give you the idea, this size, if we consider the size of, because this is a red black tree. Now, we know, if you remember how to get a sorted one, if you do the in-order traversal. So, in-order traversal means we consider this node. We first explore all the left child, then root, then the right. Okay. So, that means the whatever the size of the left of this, so after that this node is there in this sorted array. So, that is the rank of that element. So, that means if you have to find the rank of this M, that is nothing but we go to left subtree rooted at the left child, that is size of that is 5, that means total 5 elements are there. After that this, so 5 plus 1 will be the rank of this element. So, this size will give, so size of left plus 1 is the basically the rank of each element. So, that is the idea. So, let us go for the pseudocode of this. So, this is called OS select. We are finding the ith smallest element in this set S, which we have stored in this binary search tree, balanced binary search tree, which is the red black tree, with the extra that information size of a node. Okay. Now, we start with the root. Okay. So, we start with the root, then x is the root first. I mean, so tree we are outputting, we are inputting the tree also. So, this is the x is the root of the tree. Okay. Now, k we defined as, so k is the size of the left plus 1. That means, in the sorted one, if we in-order traversal, first left will be printed, then the root, then that node. So, that is the size of left plus 1, that is nothing but rank of x, the rank of the root. Okay. So, that is the first step. Now, if you are looking, if rank is say 7 and you are looking for 7th smallest element, we are done, then we return the root. Otherwise, suppose rank is 7, we are looking for 5th smallest element. Then what we have to do? We have to search the 5th smallest element in the left part of the tree, recursive call. So, recursive call, we just go for the OS select on the left, the tree, this is the tree subtree rooted at the left child of x comma I. So, this is our new root, then we will do the same thing over here. And now, suppose we are looking for, suppose rank is 7, we are looking for 9th smallest element. So, we have to go to the right part of the this, and we have to find the I minus 1th smallest element. So, this we have seen in the original select algorithm. So, done. So, this after that we will return the it will match somewhere here, and it will return the ith smallest element in the from the list. Okay. So, let us take a quick example. So, this is the root. So, we input the tree, the T is the part of the input root. So, suppose we are searching for 5th smallest element, I is equal to 5. So, now what is the rank of this? Rank of this is basically 5 plus 1, 6th. So, that we will consider. So, we start with the root, we are looking for 5th smallest element, but the rank of this is 6th, this node. So, now we have it did not match. So, we have to go for the further call. So, then we go for the here. So, we have to search the 5th smallest element in this subtree rooted at this C. So, then we call this again this OS select on the tree subtree rooted at this. If you do that, this is our new select algorithm where we have same I is 5, and now what is the rank of this node? It is the size of the left is 1, there are only 1 plus 1. So, this is 2, rank of this node is 2 in this subtree, in this subarray, if you remember. So, now, but we are looking for 5th smallest, we have reached to, this is 2nd smallest. So, now we have to go for this part, and this part we will go look for not 5th smallest, we have already reached to 2nd smallest up to here. So, we have to look for I minus k, that means 5 minus 2, third smallest element in the left part. So, we again call this I is equal to third smallest element, and we again find the rank of this. Rank of this is again this left plus 1, 2, again I is greater than, so we have to go for this part. Now, I is equal to 3 minus 2, 1. 1 is smallest element, and what is the rank of this? Rank of this is nil. So, 0 plus size of nil is 0 plus 1, 1. So, we got the element. So, we return H. So, 8th is the fifth smallest element over here. So, that is the code, that is the OS select. Now, how much time we spent for this search? How much time we spent for this OS select? That is the log n time, and that is why we are looking for this balanced binary search tree, and red black tree is one example of balanced binary search tree. So, this operation can be done in log n time. So, that is the beauty of this thing. Now, the thing is, as we said, this set is dynamic. So, we have to we have to see how the dynamic operation can be done. So, before that, let us talk about, instead of maintaining the size of a node, size of the tree rooted at that node, if you maintain the rank of that node directly, because rank is size of left plus 1, we can do that. But the problem is, if we store the rank in that extra field, now then when we modify it, when we insert a node, suppose we are inserting a node in that tree, in that set, a minimum element, then the rank will change for all the elements, and that operation will cost us n time, because we have to change all the n nodes rank, because if we have inserted a minimum element or maximum element, because rank will change. So, that is the problem with keeping the rank instead of subset size, okay, subtree size, sorry. Now, we have to think of the modifying operation, because as we said, this is a dynamic set. So, we have to think for deletion and insertion. So, then we have to think how this size, this extra information can be handled in the same time of insertion and deletion operation should take for red black tree. That we have to take. We should not spend some more time to maintain that extra information like size of the tree rooted at that to maintain that. If we spend more time, then this data structure augmentation is not useful. So, that we have to see whether we are doing that. Suppose we given this set, we have already seen, suppose we are going to insert a new node, a record came whose key value is k. So, how to insert? This is a BST insert. We can just do the insert like this. So, k is less than m, it will come to here. So, binary search tree insert. So, it will come here. So, k is greater than c, it will go there, k is greater than f, it will go there, k is greater than h, it will go there, and it will insert. So, until we reach to a nil node. Now, then we put the size of k is 1, and then we have to maintain the size along with this path, and this path will be height, that is the log n. Now, the thing is, we do not forget that the red black tree insert and red black tree delete may also need to modify the red black tree in order to maintain the balanced, and this modification will be done using the recoloring. Recoloring will not affect in the size of that extra information field, and the rotation we have seen, because sometimes we need to rotate it because to maintain the this height balance. So, that we have already seen in the red black tree insertion. So, that rotation, the structure, the rotation operation should not take more time to maintain this extra information. So, that we have to see. So, fix up subset size, subtree size should be in linear way, I mean should be in constant time, like rotation is in constant time. So, that we have to see. So, how to ensure that? Suppose this is our, we want to apply rotation on this. So, we want to make C up, E down. So, that is the left rotate, right. So, C up, E down, then how this so this will change some pointer, because this is, if you remember the rotation operation from the red black tree last lecture, this was alpha, this is beta, this is gamma. So it will, alpha will be with this and beta gamma will be hanging with this node. Okay. Now how to, so that will be changing some pointers, parent pointers, left pointer, right pointer, so that will not cost much time. Now how to maintain this extra field, this size field? So size field is also, we can think. So this is will unchanged, this will be 7 nodes are hanging over here, and this was so this is 3 will be coming here, 4 will be going there. So now this will change, because this will be now 3 plus 4, 7 plus 1, 8. Now once this is 8, this will also not change, but we can verify this, and this part will not change, because this part is the total node is not changing here. So that will also cost 2-3 changes. So that will be also constant time. So this rotation operation can be tackled constant time in this for this extra field, the subtree size field. So this also we can fix up with the as if the pointer fixing. Okay. So that is the idea. So let us yeah. So that's why the red black tree insert and delete still run in logarithm time, because this extra field of information can be done in constant time when you do the rotation and this. So this insert and delete will be in log n time. That is what we are looking for. Okay. Now this is the methodology of the data structure augmentation. So basic idea is to choose a underlying data structure. Here in this case we have taken the red black tree for our order statistics problem, and then we determine the what is the additional information we should keep to that will help for our problem. So here we have kept the subtree size, or the total number of node in the tree rooted at that node, and then we must verify that the red black tree insert and delete and that involves the rotation operation should not take more time to fix this this extra bit of information, additional information, that we have to keep. So that we have already seen. Okay. So now this is develop a new dynamic set operation that use the information OX select that we have just now seen the algorithm. So these steps are just the guideline, it is not the rigid rule to follow. Okay. Now let us take, so this is what is called data structure augmentation. Now let us take another problem and we will see how we can use the again the red black tree as an underlying data structure to this problem. This problem is called interval tree problem. We will discuss now. Okay, so what is the problem? Problem is we have given some intervals. They are basically the time intervals, you can say. We have given some time intervals, say 7 to 10 close intervals, okay, and 5 to 11, 4 to 8 o'clock, 17 to 19, 15 to 18, so 22 to, so these are the given set of intervals, and this set is dynamic. So we have this set, any interval can join at any point of time, any interval can delete from this set. So this is the set of intervals. Now we have a query interval, say, given a query intervals, and we have to see whether we have to find an interval in this set from this set S, which is dynamic, which overlaps with I. Okay. Suppose if our intervals is say these are intervals, say our query intervals say 7 and I is 7 and 10. So with 7 and 10, which are the intervals? So 5 and 11 are overlapping. Overlapping means intersection is not null. So because 11 and 5 and 11, this interval is overlapping with 7 and 10. So we have to return one of them. Find an interval in the set which that overlaps I. Even 4 and 8 also overlap. So any one we can return. So that is the problem. That is called interval. We will see the interval tree when you draw it. So this is the problem. So we have a set of dynamic set of intervals, and we have given the intervals. We need to find an overlapping interval with this given interval, search interval. Okay. Now, for this problem we have to think for a data structure to store these intervals to implement this. Now, again we do the data structure augmentation. So, we have to take a underlying data structure. So, we take the red black tree as a underlying data structure because it is a balanced binary search tree, and the node will be keyed as the left endpoint. So, that means left endpoint means this 7. So, 7 will be one value in the key. So, that is so node will be keyed on the low or left endpoint. So, we can say low of I, high of I, or sometimes we will say left or high, something like that. So, that is the left endpoint will be the key value. So, we keyed the node, I mean the red black tree form based on this value, and we have to now consider a extra information which we should keep to that will help us in this problem, interval tree problem. So, that information we will keep as a this field. So, this is called maximum, largest value in the interval in the tree rooted at this node, including the interval. So, this is basically we store in each node x the largest value in the subtree rooted at x, as well as the interval, this is basically an interval, as well as the interval int x corresponding to the key. So, this is the left endpoint we are storing, but it is corresponding to an interval. So, that means right endpoint is the maximum value, and we have to see the value, largest value in this subtree rooted at this node. So, that is our extra information we want to keep. So, that is called M field, M of x. So, now how this M of x will be maintained? So, we had this interval. So, we form this red black tree based on this left endpoint 17, 5, 15, 4, 7, 23. So, these are the left endpoint. So, we make this, we key the node interval based on this left endpoint. So, we form this tree. This is a red black tree. So, we have seen these two nodes are red, and this is a binary search tree. Also, you can check the binary search tree property. Now, this information we need to keep. So, this is the max value of this. So, maximum largest value rooted at that's a tree, including this interval. So, this is the interval 7, 10. So, 10 is the largest value. So, 10. Similarly, this is 8, this is 23. Now, for this node we have a subtree. So, this max is 10. Now, this from this interval the largest value is coming 18. So, maximum of this 18 will be stored here. Now, similarly, this is the 8, this is 18, and this is 11. So, this is the formula we are going to use. So, max of x is basically maximum among these three values. So, high of the interval value. So, that is basically this field, and comma max of the left m left x, this value, or and m the right x. So, that is the max among these three will be the value. So, based on that we calculate. Consider this node. So, this is the high endpoint of the interval 19, and this is the max of the left 18, and this is the max of the right 23. So, maximum among these three is 23. So, that is why it is 23. So, this we want to keep. Now, we have to see whether by keeping this we can do the red black tree insert and the delete in a same time, like log n time. So, for that we need to check this extra information, how we can tackle whether when we are rotating like that. For recoloring we do not need to worry about that, but for rotation operation which we need to do for insertion or deletion to again get back the red black tree. So, that you have to see. So, rotation whether that can be done in constant time, as the rotation is done in constant time of the red black tree, because it is fixing some of the pointers. Okay. So, now suppose this is the scenario, we have this the portion of the tree. Now, this is alpha, this is beta, this is gamma. We want to make this node up, this node down. So, if you do that, it will be like this. So, this is the rotation operation. Now, this field, so this will unchanged over here, because that is the, we are not doing any change over here. 14 will also unchanged, 19 will also unchanged. Now, this field will, we have to check, we have to consider 15, 14, 9, maximum is 9, sorry 19, that 19 will be there. Again this field will also change, 30, 19 and 20, maximum of this is 30, and remaining on the top no change, because that is the, we are only locally doing this operation. So, that can be done in like changing the pointer, so constant time. So, constant time we can do this fixing. So, this extra information can be handled with the same time as theta of 1. So, that is a good news. So, that will give us the time for insert and delete in logarithm time, which we want to be in the red black tree. Okay. Now, this is the our algorithm we will discuss, which is called interval search algorithm. So, we maintain this red black tree. So, okay. Now, we are searching a interval, we are searching that we have given a input into input interval I, and we are looking for an interval which is overlapping with I, right. So, now so we start with the root of this red black tree, which is storing an interval. Now, first we will check whether this is empty or not. I mean, if it is empty, then we will return and we will say no interval is overlapping. Otherwise, we will check whether this interval is overlapping with this root or not. So, when we say a interval is overlapping with a given interval, suppose this is our I interval. Okay. Now, when it will not overlap, it will not overlap with x if x is either here or x is either here. So, x is here means the left of I sorry, this is low we are using, anyway those both are same. So, low of I, this point, this value, if it is greater than high of x, then they will not overlap. This is one condition if x is this side. Okay. Otherwise, if x is this side, that is basically the completely right side of this, then we have this high of I must be less than low of x. So, that is what is this condition. So, this both the condition means it is not overlapping with x, I and x are not overlapping. Okay. So, that is the checking. So, if this both, this is OR gate, this is OR, logical OR. So, if both are, if this or this is, if one of this is not true, that means it is overlapping. If both are true, I mean OR, either this, that means this means x is completely this side, then we do not need to check this, or if x is completely this side, then this will occur. So, this is OR gate. Okay. Now, otherwise x is overlapping. Now, if this is not overlapping, if this x is not overlapping with I, then we have to go for the left of I or right of left of x or right of x. So, this is our node x, which is the root. So, then we have to go for this way or this way. Okay. Now, when we go this way, now we have some max value over here. So, this is the max of m of left of x, this is the m of left of x. Now, if our interval I, which we are matching with the which is the given interval, if our interval I is greater than the max of left of x, if the low value of I is greater than max of left of x, that means there is no interval over here which can overlap with I, because the maximum value of this is less than low of x. So, there is no interval will be here in this subtree rooted at this, because all the maximum value are the maximum value, all the values of the interval, the high values of the interval over here will be less than low of x. So, that means there will be no interval which can be overlap with I. Then we have to go for the searching in the right part of the tree. So, that we are doing here. So, then this is recursive call, then we will, if this is true, then we will go for the right part of this tree. Otherwise, if there is some chance, then we go for the left part of the tree. So, this will continue until x is null. If x is null ultimately nil, then that means there is no interval overlapping with this. Otherwise, if this is overlapping, if these two conditions is not satisfying or condition, then we return the interval. So, that is the algorithm, that is the pseudocode for this. So, let us take some example, then it will be more clear. Now, this is our red black tree with the extra information we kept here as a max of the max value of the subtree rooted at this node. So, now suppose this is our given interval I. We are searching an interval which is overlap with this. Now, I is low of I is 14 and high of I is 16. Now, we first check whether I is overlapping with this. So, that we can easily check I is not overlapping with this, because so I is not overlapping with this, because this is 17 19 means it is after 16. So, this is completely, if I is here, this is completely this side. So, I is not overlapping with this. Now, we have to go to left or right. So, for left we have to check this one, this is 18. Now, low of I is 17. So, there is a chance. So, we will go for the left subtree. So, that is our new root now. So, this is our new root, we will go for the, so this is, we check this. So, that means x will be the left of this. So, we will go for the left subtree. Now, this is our new root. Now, again we check whether I is overlapping with this. I is not overlapping, because this node, this is completely left side of I. This is 11, this is 14. So, now we check whether we should go left or right. Now, this is 8. Now, I low value is 14. So, there will be nobody here which can overlap with this. So, we have to go to the right of right subtree of that. So, we check, we do that. Now, again here we check with this whether this is overlapping with this. Now, this is overlapping. So, we return this interval. So, that is the execution of this algorithm, interval search on this. Now, we want to see a interval which is not overlapping with any of these intervals. So, that example we will see quickly. So, suppose we have a given interval 12 and 14. We want to find an interval which can overlap with this. So, we do the same thing. We search with this is not overlapping. Now, we compare with this. So, this is 18. So, we have to go to the left, and then again we search, no, not overlapping. Then we see the 8 is less than this. So, we have to go to the right. So, this is our new x. So, now we check which are overlapping, it is not overlapping. Now, we check, this is 10 and this is 12. So, there will be nobody who will be here in this subtree. So, we have to go to the right, but when we go to the right, then there is a null, because these nils are hanging there, there is a nil. So, once we reach to a nil, we return. So, I will say there will be no interval overlapping with this. So, this is the unsuccessful kind of search. Okay, so there will be no interval which overlaps with this. Now, what is the time for this interval search? So, time is basically log n, because we are going at most to the height, and this is a red black tree, this is a height balance tree. So, this is a log n. Okay. So, to get a now suppose there are k intervals which are overlapping with this, and we want to list all of them. So, this code, our given interval search code, can return only one. So, suppose there are k intervals are there which are overlapping, we know that. Now, how to return all the k intervals? So, we can do one thing, we first execute this interval search, we get overlap interval, we delete it from the database, we delete it from this red black tree, and that can take log n time. So, again we make a search after deletion of the that overlapped interval. Then when you search it again, it will give the second interval, third interval, like this. So, this time complexity will be k log n, where k is the total number of overlapping intervals. So, this is the output sensitive time complexity. So, there are some other data structure also in this problem, that is, I think, k plus log n, this is k into log n. So, that is there. Okay. So, this is what is called interval search problem, where we have seen how we can use the red black tree by augmenting it to for solving this problem. So, the next problem we will discuss is what is called fixed universe successor problem. So, this is a very new data structure, and here also there also we will do the augmentation. So, and we will see how we can solve this problem. So, this is called fixed universe solve this problem. So, we will discuss it now. Okay. So, in the fixed universe successor problem, what we have, we need to maintain a dynamic set S of n elements, and the elements are coming from this universe. So, we know the universe where from elements are coming. So, this is say we need to maintain the n records, and the key value of the records are coming from this U. So, U is the universe where from the values element values are coming. So, that is the problem. So, that is why it is called fixed universe. So, we know the universe where from these values are coming. So, now this set is dynamic, this set S. So, this we should able to do these two operation, insert and delete. We should able to add a new element in this set or new record in this set whose key value is x. We should able to delete a record from this set, and then we should able to find these two queries, successor query and predecessor query. So, successor of an element x is basically the next, we need to find the next element in S which is larger than x. So, and predecessor is the find the previous element of previous element in S which is smaller than x. So, for example, if we have a universe say 0 to 15. So, our size of the universe is U is say here 16. So, our elements are key values are from 0 to 15 if U is 16. So, now suppose at some point of time our S size is n is 4, we have 4 records, 4 elements, and that values are basically 1, 9, 10, 15. So, this is say at some point of time. Now, if you have to find say successor of 2, 2 is belongs to this. So, successor x is 2. So, successor of 2 is basically 9. If you have to find successor of 3 is also 9. Successor of 1 is also 9. So, that is the query. So, we need to find the successor of an element x which is in U. It could be in S or may not be in S. Similarly, predecessor query we will do. In this lecture, we will study the how we can have a successor query or how we can perform this operation. So, predecessor query is very much similar. So, we need to find a data structure for this set S of n elements which are coming from this universe. We know the universe, that is why it is called fixed universe. So, that we should able to do this operation in a very faster way. So, the data structure we can think of, first data structure may be the balanced binary search tree, the red black tree, which we know these operations can be handled by log n time if n is the size of the set S. Okay. Now, but we want to do it, but here in this case we are not using this fact, we know the universe. So, without we are not using this fact, we know the universe. So, that is the thing. So, but we want to do it much more faster than this. So, what is the time complexity we want to do this query, successor query? We want to do it in log U. So, which is very fast. So, this time complexity was given by Peter van de Boas in 1975. So, he proposed a data structure which can give this time complexity for successor query. So, we will slowly learn this data structure. So, in this case we will do the augmentation. We start with the array, then we will do lots of augmentation on this. So, now the question is how we can get log U time complexity. So, log U can be achieved by, we know the log operation can be get by binary search. So, we can do the binary search on log U numbers of elements. So, that can give. Now, can you have a recurrence which can give log U? Yes. So, this is the recurrence. If t u is equal to t to root u plus order of 1, then this will give you log U, because if you can put u is equal to log U, then it will by master method we can get log U. So, we need to bring this recurrence in our algorithm. Okay, so let us start to get the data structure. So this is the starting point. We start with, we take a vector. This is a vector array basically. We take a array. This is called bit vector array of size u. So this is a, if u is 16, then our array size is 16 and starting from 0 to 15, because our universe is 0 to 15. That is the way we like C array start from 0 to u minus 1, like that. Okay. Now suppose this is our S at some point of time, S is 1, 9. So how we fill this array? We will fill this array by this u of x will be 1 if x is belongs to S. So like 1 is there, so this will be u of 1 is 1, 9. So 9, u of 9 is 1. So the array element is either 0 or 1, bit vector, power on, off. So if that person is there, we will put the light on in that room, like that. So very nice data structure, very powerful. So how we can insert in this data structure an element? Suppose we want to add 8 in this set S. So what to do? We go to u8 and we make it 1, constant time. Suppose we want to delete 9, 9 is already there. So how to do? We go to u9, this field we delete, that make it 0. So just theta of 1 time. Now, but the question is how we can do the successor query. Suppose we have to do the successor query of 2 or 1. So that means we need to scan this array, because we do not know where is the next one. So we need to find the next one in this array. So that may cost us, that will cost us order of u time in the worst case, because in the worst case we need to scan the whole array of size u. So that is the worst case, but we want to do it in log u. Basically we want to bring that recurrence where we can bring it to be root u. Now the question is how this array can be break it into root u. So that is the concept which we can bring. We divide this array into sub arrays like blocks. I mean this is one dimension array. We can so this is of size u. How to bring the root u? We can think of a matrix of root u cross root u. So this is just 16, so 4 by 4. So we can break this by vz. So this is first vz or first subarray, first block. This is next 4 is the second vz, like this. We will break it into the subarrays. So that is the idea. We will break this array or universe into the vz or the subarrays or the blocks. So then this is the, how many vz will be there? We have total size u, then there will be root u vz, and each size of the vz will be root u. Then it is basically a matrix you can think. You can just think of a 2-dimensional array in C. So it is basically a root u cross root u matrix. So it is basically u. So this is the first row, this is second row, I mean 0th row w0. So the 0th vz, this is 1th vz, like this. So this is the way we represent this. So thus we are breaking this into the vz, and this is the representation. This is the first vz, 0th vz, w0, w1, w2, w3, and these are the already numbers are there. So we have 1 in those positions and 0 in the remaining position. Now the question is how we will do the insert and delete. So this is the general form. We have for general u, we have this many vz, w0, w1 up to w root u minus 1, and each size of each vz is 0 to root u minus 1. So that is just the generalized version of this example. Now the question is how we can insert an element in that. Suppose we have to insert a 9. So we have to find the position of 9 in this sub vz. So how to find the position of 9? We want to take this 9 and we want to convert this into binary, and the first half of this we call is high, because 9 binary representation is 1 0 0 1. So first half is 1 0. So this is basically 2, and this high of x will represent the which number vz will go for. So this is basically we will go for w2. So 9 then this low of x is the next half. So this is 0 1, this is 1. This is the, yes, so that will be the position in that vz. So this is 0 1 2 3. So this is basically our x 9. So, we can go to this field and we can if 9 has to insert, we can insert 9 there. So, this is the way. So, we defined high of x, low of x, and where high is x equal to high of x into root u plus low of x. So, this is just a, you can think of we write x in a binary and high of x is the first, I mean half of the least significant bits, and the low of x is the this remaining sorry, most significant bit is the high of x, low of x is the least significant. And this way we get the low and high for every x. For x equal to 2, that is 0 0 1 0, x equal to 2. So, that will be 0 0 means this widget, and 1 2 means it will be here. So, this is basically x equal to 2 position. So, this will continue. So, this is the way, and also suppose we are finding the say for example, suppose we are finding the successor of x equal to 2. How to do that? So, we first break it into half half, like high of x, low of x. High of x of 2 is 0 and low of x is 2. So, this is the, so 2 is basically here. So, x equal to 2, the position in this array is here. Now, we are finding the successor of this. So, first what we will do? We first find the successor of x after low of x in that widget. Okay. But here we have 0 over here. So, there is nobody, this is for 4, we have a large. Now, next, so we have to look into the next sub array or next sub widget. So, that is this one, but there is nobody here which is 1. So, we are looking for a next one basically in this arrangement. So, here there is no ones, all are zeros, but we are scanning. So, that will cost us again root u time. So, we to avoid that, we want to do a augmentation on this data structure. We will maintain a extra array over here, that is a array of size root u again, because this is a, for each sub widget we have a this field. So, this field will indicate whether this is empty or not. If all are 0, this field is empty. If some ones are there, at least one ones are there, that is 1. So, because this here all are 0, so this field will be 0, and this 1 is there, we have 1, here we have 1, we have 1. So, what is the advantage of this array, non-empty array, or we will later on we will refer as a summary array? Advantage is we will just check the, when we are looking for the next one in the next sub arrays or sub widget, we just do not look into those widget, we do not scan into those widget which is having 0 over here. So, that means we are going to look in, we are going to search for a next non-empty widget. So, that we can do by again the successor query on this array, on this non-empty array or the summary array. So, that we will do. Okay. So, insert is we know insert, we can go to that position and we can insert, and that is constant time. So, we are worried about the successor. So, successor of x, as we said, we first look into the successor of x within the widget w of high of x, okay, starting after the position low of x. Okay. So, after the position low, because after low of x in that block we need to find a 1. If we get it, we return it. If we do not get it, then we have to find the next non-zero widget. So, after high of x is the that corresponding widget. So, that we will do, and suppose I is the widget which is having the non-zero element. So, there are some ones in that widget. So, then we get the smallest element in that widget. So, we want to see this. So, what is the time complexity for this? This is size is root u, so order of root u. This again the non-empty search, non-empty array is also root u. So, this is also order of root u, this is root u. So, this is a order of root u, but we want to bring it into a recursive form. So, how we can think for a recursive form? This is, we can think of a recursion, I mean the recursive call, successor of x, comma w we can say. Now, here this is also a successor call, you can think, because this is a sub widget of W high. So, here we are looking for a 1 after low of x. So, that is a successor call. We can have a successor of low of x comma W high. Then if found okay, otherwise we are having this is also successor call, because that non-empty array, that is also array. So, we are looking for a next one after this high of x. So, that is also successor call, and once we get that I, then we know that Vz is non-empty. So, we need to find the first smallest one. So, smallest one means that is also successor call of say some minus term, minus 1, because the array start from 0 1 like this. So, that is also successor call of minus 1. We in this case we use minus infinity. So, successor of minus infinity in that widget. So, this is the sub widget which we have already discussed. So, this is just the generalized representation of that, and this non-empty array we replace by the summary array. This is the summary array. So, this is the picture. So, we are seeing this arrays, the sub widget as a 2-dimensional array. This we are viewing. So, we know this is the how we represent the 2-dimensional array like in C. Okay. Now, this S is this set, suppose. So, these are the position where 1 is there and remaining we have zeros. Okay. Now, suppose we want to insert a element x. So, what we do? We calculate this. So, we break it into binary, and then the first most significant is the high of x, and the half of least significant low of x. So, we go to that position, and so we got the widget number where x is, the x will be going. So, in that we put the summary bit to be 1, and then we go to that position. So, W of say for 9 we have this here, we go to the this position and we insert like this. So, this is the summary bit, because there is a 1 we put it 1. This is also array. Now, how we can make use of this to have a successor call. So, successor of this, so we just suppose we have to find the successor of 2. So, what to do? For 2, this is high of x is 0. So, that is this widget we are in. So, we find the successor, and for 2 low of x is 2. So, we try to find the successor in this widget after 2. So, that is a successor call. There is nobody. So, we have to go for another successor call on this sub array, on this array of summary array. So, that is after high of x. So, that is we are doing. So, this is the successor call low of x in that widget, and this is the successor call in the summary bit or non-empty bit after high of x. So, that is I, basically I is the widget number where we have a some 1 is there, I mean at least 1 is there, that is the non-empty widget. So, then we have a successor call of in that widget we want to find the smallest one. So, for that it is again a successor call of some minus term, minus 1. So, we use the minus infinity, and then once we get that value we return this as I into root over of this order of W. This is basically U in our notation plus J. Okay. Now, there are 3 calls over here. So, that is why it is basically Tu is equal to 3 T root U plus, but we want only one call, because we want this to be log U. So, how we can reduce this 3 call to 1 call? So, that we will see. Now, 1 call we are looking for, we do not want these 2 more calls. So, how we can achieve that? Now, here if you remember we are doing the first successor call. If we are say here in this picture, we are doing the first successor call over here. If we are getting okay, then 1 call we stop. If there is no 1 after this low, then we are going for this successor call. And once so how to avoid, how to do this this thing, that we will not go for a call over here. Now, we will do another augmentation on this data structure. Suppose we want to store the maximum index where 1 is in the maximum index. So, then we can save that, we will come to that. Let us take that picture. Yeah, so maximum value will store. Yeah, so this is more augmentation we are doing. So what we are doing here, we are storing the maximum. This is the extra augmentation, extra array, max array of the same size root u. So this indicate where is the maximum index, where is the last one. So here it is only 1 1. So this max is 1. So this you for the timing you do not consider this. So this is the one. Now here there is no 1, so we will make this empty, or we can have some dummy. So here max is at 2. So this is 0 1 2. Okay, like this. Now what is the advantage of this? Suppose we are doing a successor call of 2. So 2 means high is this. So we are at that with this the widget w0. Then we check the maximum. Maximum is 1. So we know by seeing this maximum, there will be no 1 after 1. So we will not go for the successor call in this. Then we will directly go for the successor call for this summary array, and that will give us the next I, which is next widget number where this 1 is. Now, so in that case again, so we have to go for a successor call in here. So 2 call. So we want to avoid that also. For that we bring the minimum. So we need to get this. This is a successor of 2. So to get this, if we can store the minimum also. So this is the minimum, where is the first one is. Then we can return that value. This is the index, and that is the answer. Return that value. So that way we are only did the one successor call. So one successor call will be here. If the low of x is less than max, then we know there is a 1 after low of x. We will do the successor call, and definitely we will get the 1. We will get the index there. Otherwise, if low of x is greater than max, then we know there is no 1 over here. We will go for the summary bit, which where is 1, that successor call we need to do. But again we do not want to do any successor call there. This minimum, where is the first one, that index we will return. So that way we will do that. So that is the algo we will do. So we have 2 more array, max array and min array, where we will store this, and we will reduce the we will do it by only one successor call. So that is the, and this insert also we need to maintain there if we want to insert something. So we need to change this mean and maximum field also, these 2 new field. So this is the final improved successor call. So here we have only one successor call, and so this is the time complexity of this. Okay. So in this lecture we have covered the data structure augmentation. We have seen how we can do the augmentation of a existing data structure to solve our problem. So thank you very much.